Inside a factory in Cincinnati, a single piece of metal takes 60 days to make. 60 days for one blade. But here's the impossible part. This blade operates at temperatures that should melt it. It spins faster than a bullet travels. And if it fails, it doesn't just break. It explodes with the force of a grenade, yet it never fails. How is that possible? How do you build something that survives conditions that should destroy it? The answer starts with a secret mixture. Titanium and aluminum, combined so precisely that a variation of 0.1% ruins everything. The melting point is 1,650 degrees Celsius. The blade operates at 1,400 degrees. That leaves a margin of error of just 200 degrees. 200 degrees is less than the difference between boiling water and a hot summer day. But temperature isn't the real problem. The real problem is the force. At full power, the tip of this blade moves at 1,500 miles per hour, faster than sound. The centrifugal force pulling on it equals the weight of a fully loaded Boeing 737. Imagine holding up an entire airplane with your bare hands. Now imagine spinning in a circle 1,000 times per minute while doing it. That's what this blade does, continuously, for years. But there's something even more impossible about this blade. Something that defies the laws of physics. In segment 2, we'll see what happens when you try to build something that shouldn't exist. The blade starts as a solid block of titanium weighing 200 pounds. Through forging, machining, and grinding, 90% of that metal is removed. 180 pounds becomes scrap. But here's the problem. The blade can't be solid. A solid blade would be too heavy. The engine couldn't spin it fast enough. It would tear itself apart. So the blade must be hollow. But not just hollow. The inside must contain a lattice structure, a honeycomb pattern thinner than a human hair. This reduces weight by 40% while maintaining strength. The wall thickness is just 2 millimeters. 2 millimeters of titanium separating supersonic rotation from catastrophic failure. Now here's where it gets impossible. To hollow out the blade, you can't use a drill. A drill would vibrate. It would crack the thin walls. It would ruin the blade. So engineers use electricity, electrical discharge machining. A copper electrode is submerged in fluid. Electrical sparks erode the titanium away, 1 micron at a time. No physical contact. Just pure electrical erosion. The process takes 18 hours per blade. 18 hours of sparks eating metal. The electrode moves to within half a micron of precision. That's 500 times thinner than a human hair. But even after 18 hours of electrical erosion, the blade still isn't finished, because there's another problem. A problem that should make the blade fail in just a few hundred hours. In segment 3, we'll see what destroys these blades and the 3-micron secret that prevents it. The blade is hollow, it's shaped, it's precise. But it has a fatal weakness. Rain, dust, ice. At 500 miles per hour, every raindrop hits like a bullet. Every grain of sand is like a tiny bomb. Every ice crystal is a chisel. Without protection, the blade would erode in just 500 flight hours. 500 hours. That's less than 1 month of commercial flying. So the blade needs armor, but not just any armor. The armor must be harder than diamond, lighter than paint, and just 3 microns thick, 3 microns. 3/1000ths of a millimeter. Thinner than a soap bubble. The coating is titanium nitride, a ceramic applied in a vacuum chamber. The blade is heated to 450 degrees. Titanium and nitrogen are vaporized and ionized. The ions are accelerated toward the blade, bonding at the atomic level. The coating is harder than diamond. It protects against erosion for 50,000 hours. 100 times longer than without it. But here's the terrifying part. If the coating is too thin, the blade erodes. If it's too thick, it flakes off. The tolerance is 0.5 microns. Half a micron. Apply the coating wrong and the blade fails. Not immediately. Not obviously. But after 6 months of service, the blade develops a crack. The crack spreads. And then, without warning, the blade explodes. So how do they know the coating is perfect? How do they inspect something 3 microns thick on a blade with curves and angles? In the final segment, we'll see the inspection process that catches defects smaller than a bacteria and reveal the staggering truth about what it takes to build one engine. The blade is finished, coated, protected. But is it perfect? Time to find out. Each blade is inspected with a coordinate measuring machine. A probe touches 5,000 points on the surface, checking dimensions to within 1 micron. 1,000th of a millimeter. The blade is scanned with X-ray computed tomography, a CT scan for metal. The machine reconstructs the internal structure in 3 dimensions. It checks for voids, cracks, and wall thickness variations. Any defect larger than 50 microns is rejected. 50 microns? Half the width of a human hair. The surface is inspected under microscopes at 1,000 times magnification. The coating thickness is measured with eddy current sensors. The balance is checked on a spin rig. The blade must be balanced to within 0.1 gram centimeters. That's like balancing a 20-pound weight with a single grain of sand. Now here's the staggering truth. One engine has 22 fan blades. That's 1,320 days of manufacturing time, almost 4 years just for the fan section. The cost of one fan blade? $30,000. The fan section alone costs $660,000. But the real cost isn't money, it's precision. 60 days of manufacturing, 2 mm walls, 3 micron coating, 1 micron tolerance, half a micron balance. All of this just to keep the blade spinning, to keep it from exploding, to keep you alive. A complete jet engine has over 25,000 parts, each one manufactured to similar tolerances, each one inspected with similar precision, each one critical. When you board a plane, 22 blades are spinning at supersonic speed, holding back forces that should destroy them. And they don't, because 60 days of manufacturing, 1 micron of tolerance, and 3 microns of coating stand between you and catastrophe. This is how the impossible is built. At Dark Whisper, we reveal the machines that keep you alive. Tomorrow, we enter the heart of the engine, the turbine blades that survive temperatures hotter than lava. Subscribe to see the full series. I'm Dark Whisper, and I'll see you in the next investigation.